Okay. Yeah, thank you for the introduction. My name is Iman Marvian. I'm based at Duke University in North Carolina. And in this talk, I present some results in an ongoing project in my group on quantum control in the presence of symmetry and locality. So the basic question is what happens if all the Hamiltonians that we can implement are local. For example, they act on two or few qubits or subsystems. And if they respect certain symmetry, for example, they are all rotationally invariant, then which unitaries we can implement, what states we can prepare, how long does it take to prepare those states, and those sorts of questions. Some of the questions that I study can also be phrased in the language of quantum circuits. Sorry, do I have a pointer here? Or? That's fine if there's a, so some of the questions that I study can also be phrased in the language of quantum circuits. For example, oh, I see. Okay, perfect. Thank you. So yeah, some of the questions that I study can also be phrased in the language of quantum circuits. For example, I study circuits that are formed from two local gates or k local gates that all respect a certain symmetry, such as rotational symmetry. Okay. So of course, in the absence of symmetries, this problem is very well understood. We know that from results of David DiVincenzo and Seth Lloyd from 94 and 95, we know that any unitary transformation on n qubits or n qubits can be implemented by finite sequence of two local gates that acts only on a pair of qubits or qubits. And this result was, of course, discovered in the context of quantum computing, but in my mind, this is a much more fundamental facts about dynamics of quantum mechanical systems. We know that locality imposes a lot of constraints on the time evolution of composite systems. For example, locality implies finite speed of propagation of information, as it's highlighted, for example, by Lieb-Robinson bound. But this result, this the universality result, implies that despite all those constraints on the short-term time evolution of the system, if you give the system enough time, then it can experience any arbitrary unitary evolution. In other words, the long-term time evolution of the system is not restricted by locality alone. Locality doesn't restrict possible time evolution of a system, and it can experience any arbitrary unitary evolution. Now, one basic question that I like to study here is, what happens if you have both locality and symmetry? Clearly, if all the gates in this circuit respect a symmetry, for example, they are all rotationally invariant, then all the unitaries that you can implement also have that should respect that symmetry. There's nothing to break that symmetry. Now, one basic question here is, can I implement all unitaries that respect the symmetry using local unitaries that respect the symmetry or not? In other words, do local symmetric Hamiltonians generate all symmetric unitaries or not? Okay, so this is just the basic question, and I formulate it later more precisely. So here is an outline of my talk. I will start by talking about some motivations and applications. Then I will present a kind of surprising strong Nogo theorem and about non-universality of local gates. And then I will talk about specific examples of U1, SU2, and SUD symmetry in general. And then we will see also a kind of surprising distinction between SUD symmetry for d equal to 2 and d larger than 2, for example, d equal to 3. So these results are partially based on these three papers. The second and third paper are in collaboration with two bright students at Duke University, Austin Hals and Han-Ching Liu. Okay, so let's talk a little bit about the motivations. Why we study local symmetric quantum circuits, why we study Hamiltonians with locality and symmetry. First of all, the notion of local symmetric quantum circuits has already become a standard toolbox in theoretical physics. People use it, for example, to classify phases of matter. Symmetry-protected topological phases of matter are classified based on the equivalency classes defined by load-up symmetric circuits. They are also used, for example, to study chaos in the presence of symmetries. And so I would say it's kind of embarrassing that we still don't know we can't still answer some basic questions about these properties of these circuits, given that they have already become standard tools in theoretical physics. But there are also more specific motivations and applications of studying this. topic. First of all, perhaps we can find new conservation laws. Standard conservation laws that we know they hold because of the symmetry, for example, conservation of angular momentum that holds because of rotational symmetry, but they don't, they hold regardless of locality. Now the question is, are there any additional type of constraints, additional type of conservation laws that hold because you have both symmetry and locality together? And that probably can help us to understand the dynamics of a complex system better, basically. The second motivation comes from the field of quantum thermodynamics, quantum resource theories, quantum reference frames. In all these areas, we often assume that we can implement a symmetric unitary. For example, in the context of quantum thermodynamics, we often assume that we can implement an arbitrary energy conserving unitary with negligible thermodynamic cost, right? And regardless of the number of subsystems, you can imagine that I have n arbitrarily large number of subsystems. Still, we assume that we can implement an arbitrary energy conserving unitary on them. And the question is how we can implement it. If I'm restricted to implement local unitaries, then maybe there is some, and I want to implement local energy conserving unitaries, then maybe I cannot implement a general energy conserving unitary. And then maybe there is some hidden thermodynamic cost that I have to take into account when I know that the interactions are local. And the third motivation that I discussed in the paper, but I don't have time to go through it in details here, is about synthesizing noise-resilient quantum circuits. Generally, we can take advantage of symmetries to design circuits that are resilient against certain types of noise. And so that's another type of motivation to study this general problem. Now, let's try to formulate this problem more clearly. So here, I will focus on an example of U1 symmetry. So this will be the running example throughout my talk. So suppose I have n qubits, and here the symmetry is rotation around Z. So Z here is Pauli Z operator, and I'm interested in unitaries. I'm interested in unitaries that commute with the action of symmetry. So you are applying the same rotation on all qubits, and so V is invariant under this global rotation, or equivalent to unitaries that conserve total angular momentum in Z direction, or Hamming weight of bit strings. These are all equivalent ways to define it. So let's look at a few simple examples. In the case of n equal to one qubit, this will be all diagonal unitaries, the unitaries that are diagonal in the computational basis, 0-1 basis. In the case of n equal to 2, I have 3 sectors, sector with Hamming weight 0, Hamming weight 1, and Hamming weight 2. And then a general U1 invariant unitary will be an arbitrary phase in this sector with Hamming weight 0, and an arbitrary 2x2 unitary in the sector with Hamming weight 1, and arbitrary phase again in sector with Hamming weight 2. Okay? And you have a similar thing in the case of n equal to 3, except now you have 4 sectors, 4 sectors with Hamming weight from 0 to 3. Okay? And now I can ask the most basic version of the question that I want to study here. The basic question is, can I implement a general unitary that respects the symmetry on 3 qubits using unitaries that act only on 2 qubits? So this is a question about 8x8 matrices, basically. So I have matrices that are, I want to implement a general matrix. I want to implement a general unitary transformation in this form using unitaries that are in this form, tensor product identity, basically. Okay? So just a basic question about 3 qubits, which is still non-trivial. Okay, so here is a strong Nogo theorem. It turns out that in the case of continuous symmetries, such as U1 symmetry, the answer is no. You cannot implement a general symmetric unitary using local unitaries. And okay, so you may say maybe I cannot implement them exactly, but maybe perhaps I can implement them approximately. Again, it turns out the answer is no. It turns out that the group of all symmetric unitaries and the subgroup generated by k local symmetric unitaries, they are both compact connected Lie groups. And this means that basically the relation between the two groups can be understood based on this schematic figure. So here the torus represents the group of all symmetric unitaries, and the helix, the blue curve on this torus represents the group of the subgroup generated by k local symmetric unitaries. So there are points on the torus that you cannot get arbitrarily close to them. Okay, so that's the point. And it turns out that the gap between the dimension of these two manifolds constantly increases with the system size. So the situation becomes worse and worse as the system gets larger. Okay, let's think about this U1 example again. This is, I showed that the difference between the dimension of these two manifolds, this is the manifold, again, this one is the manifold of unitaries generated by k local U1 invariant unitaries. So this is a subgroup of all U1 invariant unitaries that you can generate by k local U1 invariant unitaries. And sorry. So the difference between the dimensions of these two manifolds is exactly n minus k. N is again the number of total qubits, and k is the locality of gates that you can implement. Okay. So for example, in the case of that simple example that I discussed at the beginning, 3 qubits, it turns out that the group of all symmetric unitaries, this one is 20-dimensional, whereas this one, the one that can be implemented by 2 local unitaries, is 19-dimensional. So 20 minus 19 is equal to 3 minus 2 in this case. Okay? And just to have an example in mind, the family of unitaries e to the minus I theta z tensor 3, the unitaries that are generated by Hamiltonian z tensor 3, cannot be generated by using 2 local U1 invariant unitaries, except a few points such as theta equals to 0, for example. Okay, so the similar result holds in the case of SU2 symmetry. In the case of SU2 symmetry, the difference between this dimension of these two manifolds turns out to be exactly equal to integer part of n half minus integer part of k half. And so, for example, if you think about n equal to 4 qubits, okay, sorry, I see something is lost here. So, okay, so there is a figure here that is not shown, but so in the case of n equal to 4 qubits, there is this example that is not shown here in PowerPoint. You can show that this simple Hamiltonian, that is the swap Hamiltonian, that swap the state of the first pair of qubits with the second pair of qubits. This swap Hamiltonian is a unitary transformation, but it's also a Hermitian operator, so I can think of it as a Hamiltonian. So this cannot be realized using 2 local gates. In other words, you can realize it using Heisenberg exchange interaction. Okay, so this is another simple example. And so again, in the case of this n equal to 4 qubits, it turns out that you have, if you can implement the Hamiltonian using 2 local gates, then the Hamiltonian should satisfy this extra condition. So this condition is basically an inner product of the Hamiltonian with the projectors to different sectors with different angular momentum, basically. I don't discuss much about this constraint, in the interest of time. But if there are questions, I can come back to this. There is a general bound also on this. There is a general bound which this is basically a lower bound on the difference between dimension of these two groups. So and so it turns out that the difference between the dimension of these two manifolds for a general group is basically lower bounded by the difference between the number. So this number irreps of Gn is the number of total inequivalent irreducible representation of group G that appear on n subsystems, and this irreps of Gk is the total number of inequivalent irreducible representation of group G that appears on k subsystems. So for example, if again we go back to our U1 example, in the case of U1, inequivalent irreps are labeled by Hamming weight of the sector, basically. And so in the case of n qubits, I have Hamming weight from 0 to n, so n plus 1 different Hamming weights. And on k subsystems, I can have only k plus 1 Hamming weights. And so the difference is just n minus k. It turns out that this lower bound, this general lower bound, holds as equality in that case. In the case of U1 and SU2, it holds as equality. But the point here is, this lower bound, this increases for continuous groups, the number of inequivalent irreps that appear on n subsystems constantly increases with the system size, and so this lower bound increases with the system size, and so there is no finite k for which you can achieve universality. That's the point. And roughly speaking, to have some intuition about what is the quantity in the right-hand side, you can think of it as basically the difference between the total charge in the system, the total charge that can be allowed in the system, minus the total charge that can participate in an interaction with k qubits or k subsystems. Okay. Now, this result was kind of surprising and kind of made me worried, because I work on quantum resource theories, on quantum thermodynamics, on resource theory of asymmetry, quantum reference frames. And in all of these theories, again, we assume we can implement all these unitaries, symmetric unitaries with negligible cost. And this theorem tells me that I can't implement them using local symmetric unitaries. Fortunately, it turns out that at least in some cases, we can circumvent this Nogo theorem using ancillary qubits. So in particular, it turns out that, sorry. So it turns out that in the case of U1 symmetry with qubits, I can implement an arbitrary U1 invariant unitary using only x plus y interaction, which respects the symmetry and is too local, provided that I can use a single ancillary qubit which is initially prepared in a state 0. So I bring a single ancillary qubit which is initially in a state, prepared in a state 0. I interact it with my n qubits, and then I return it in its initial state. And then you can circumvent all those constraints. Remember, in the absence of this, in the absence of ancillary qubit, the difference between the dimension of these two manifolds was n minus k, meaning that even if I act with n minus 1 local gates, I cannot still implement all n local gates, right? Without using ancillary qubit. Just using n minus 1 local gates, I cannot implement all n local gates. But here, just using a single ancillary qubit is enough to implement a general unitary using just 2 local gates, basically. Okay. In the context of quantum thermodynamics, of course, the Nogo theorem that I showed before, it implies that generic energy conserving unitary cannot be implemented using local energy conserving unitaries. But you can basically show that if you allow me to use a single ancillary system or a catalyst in this context, then I can circumvent the Nogo theorem. In particular, here is a theorem. Consider a finite set of closed systems with the property that for each system, the gap between any consecutive pairs of energy levels is delta E. Then any global energy conserving unitary transformation on these systems can be implemented by a finite sequence of 2 local energy conserving unitaries, provided that one can use a single ancillary qubit or catalyst with energy gap delta E. So the energy gap here in the catalyst should be equal to the energy gap in this system. Okay. So this was about U1 symmetry. Now, how about SU2? In the case of SU2, again, it turns out that you can circumvent all these constraints. And in particular, you can implement a general rotational invariant unitary using just Heisenberg exchange interaction, which is 2 local and rotational invariant, provided that now I can use 2 ancillary qubits. The 2 ancillary qubits can be, for example, initially prepared in a state 0, 0, or any state restricted to the symmetric subspace, the 3-dimensional symmetric subspace, the triplet subspace, basically. It can be even a mixed state in the triplet subspace, or it should be in this antisymmetric subspace. Okay? Now, so this was about U1 and SU2. The next step is to study SUD, of course. And so we study qubit circuits with, that are formed from 2 local gates with SUD symmetry. So here, parameter D specifies both the dimension of these local subsystems and also specifies my symmetry. Okay, and so 2 local gates can be all written in this form: e to the I theta PAB. PAB is swap. So up to a global phase, any two local SUD invariant gate on qubits can be written in this form. And so basically, we are studying circuits that are formed from these gates for different values of theta and for different pairs of qubits. Or equivalently, we study Hamiltonians that can be written in this form, the Hamiltonians that are linear combination of just swap operators on different pairs of qubits. And then we found a surprising result. We found that in the there is an important distinction between d equal to 2 and d larger than 2. In particular, in the case of d equal to 2, we found that all the constraints that are imposed by locality, additional constraints that are imposed by locality, are essentially constraints on the relative phases between sectors with different angular momenta. Inside each sector with any fixed angular momenta, you can implement an arbitrary rotationally invariant unitary. There are no additional constraints. On the other hand, when you go to d equal to 3 or larger, then there are also additional constraints inside each sector, right? And to highlight this, I have an example here. interesting example. So this is an example about D equal to 3, SU3 symmetry with Q treats. So I assume I have 6 Q treats. 3 of these Q treats are prepared all in a state 0, and the other 3 are prepared in a singlet state, so the totally antisymmetrical states of these 3 Q treats. And so then it turns out that the joint state of these 6 Q treats is restricted to a sector with one irreducible representation of the symmetry. So you don't have superposition between different sectors. Now, what's interesting about this example is that if you look at general SU3 invariant unitaries, then you can show that this transformation, you can start from this state, this initial state, and create any superposition in this form. So here I have superposition of the original state, so alpha singlet tensor 3. This is my initial state. And the second state is the state that is obtained by basically swapping the first 3 Q trees with the second 3 Q trees. Okay? So you can create arbitrary superposition of these states using a general SU3 invariant unitaries. That's not hard to show. We can write an explicit SU3 invariant unitary that realizes this transformation. On the other hand, if you restrict me to use only SU3 invariant unitaries that can be implemented with 2 local SU3 invariant unitaries, then I have a very strong restriction. From this initial state, I can only go to, I can't generate an arbitrary superposition in this form. I can only prepare the original state, obviously, because I can just do nothing. Or I can swap the first 3 Q trees and with the second 3 Q trees, and I can obtain this state, 0 tensor 3 tensor singlet. But I cannot generate an arbitrary superposition of them. So here you see that locality imposes a restriction on the possible realizable state transformations, right? This doesn't exist, of course, in the absence of symmetries. And finally, the interesting point is, if you now allow me to use another 3 Q trees, which is initially prepared, which are initially prepared in the singlet state, then now I have 9 Q trees. Now I can use this new 3 Q trees as a catalyst, and I can realize this transformation. I can overcome the constraints imposed by symmetry, and I can transform, using just 2 local SU3 invariant unitaries, I can create an arbitrary superposition. So now this, this new 3 Q trees acts as catalyst, and they allow me to implement this transformation and overcome the constraints imposed by locality. Okay, so now we can understand this, basically this constraint based on a new conservation law. I don't have time to talk about this new conservation law, but let me give you briefly. So there are various conservation laws, but there are basically 2 types of conservation laws. But let me give you intuition about one of, an example of them in just 1 minute. So it turns out there is a Z2 symmetry in this context. So if you look at this unitaries that I can implement, so e to the I theta swap can be written as linear combination of identity and swap. Now, if you look at this combination, the first term here is a real term. If I write it, for example, in the computational basis, it's a real matrix with, and I is an even permutation, whereas the second term here is an imaginary coefficient, and swap is an odd permutation. Now, so you have basically this coupling between even parity and real coefficient, and odd parity and imaginary coefficient. And then, when you multiply these matrices, this pattern remains valid. So you always have, even parity terms, even parity in terms of permutations with real coefficients, and odd parity terms with imaginary coefficients. Now, it turns out that this constraint, of course, understanding this constraint is non-trivial because permutations are in general linearly dependent, but we can still understand this constraint. And so basically, it turns out that there are new conservation laws that correspond to this constraint. For example, just let me finish with this example, basically. So it turns out that this function remains conserved because of this particular Z2 symmetry. This is a summation over the expectation value squared of all permutations. So the summation is over all permutation, Sn, the group of all permutations. And this SGN is just a parity, which is either +1 or -1. And it turns out that this function is conserved. So I don't have time to explain more about it, but I'll be happy to answer questions later. In general, it turns out that there are essentially 3 types of constraints on the relative phases between sectors with different erupts, the Z2 type constraint that I just explained, and finally, a constraint that is obtained by mapping the system, Q-the system, to a free fermionic system, basically. So you can show that dynamics in certain sectors is described by a free fermionic Hamiltonian. So my time is over, so let me stop here, and thank you for your attention.